Okay. Looks like we have reached some sort of. Okay. Okay. So this is basically the labeling idea, and I was essentially asking you. So there were basically two things that they are talking about: the simple case of level propagation, the more complex case of level propagation. Here, essentially, these two guys are hoping that one of the other guy will change its value, and when neither of them can change their values, then they know that they have both reached their value and converged to their value. Okay. Okay. The interesting thing about the LRTDP actually is just like so normal value iteration has no convergence guarantee. I mean, there is no finite time convergence guarantee. Policy iteration does converge in finite time. Value iteration doesn't have to, although it actually works quite well in practice. Okay, and one of the things that because he's doing the labeling procedure, and since there are only finite number of states, eventually the converged, basically the initial state would be labeled as converged, at which point you're done. Okay, and so because of that, LRTDP actually has finite time convergence guarantees. And furthermore, the other thing is it focuses in doing the exploration of the space. It's focusing on states that are not converged, because it's the ones that are converged become part of the terminal states. Okay, so those are two reasons why it's actually quite efficient. In particular, compared to the synchronous value iteration, where every state's value is updated in every iteration. Okay, whereas this is quite different because. Okay. One other question is. Actually, this will skip. I don't think this is not in the paper that you read, but one of the extensions of LRTDP was to actually provide both an upper and lower bound for the true value of a state. Okay, and once you have both an upper and a lower bound, in a minute I'll talk about the lower bound, and then it turns out you can also compute upper bounds that way. And once you get that, then you can use the spread in the upper and lower bound to decide how close to convergence that particular state is, and focus your exploration on the states that are not close to convergence. That way, that's one of the ideas that can be done. But that's something that is not in the paper that you read. Okay. There is one thing else I should mention. The Mausam book. Awesome and Colabo. How many of you have actually managed to look at that book, Mausam and Colabo book? That's kind of depressing. There is, I mentioned the Morgan Claypool booklet on Markov-Dacian processes by Mausam and Colabo.
Oh, yeah, I
right?
It's
okay.
Like a thesis.
What?
It's like a thesis.
It's a monograph.
Okay.
But they are the state of the art in some sense. So it's better than papers, because individual papers just talk about one specific extension. Textbooks will wait for the entire field to converge before they start writing the textbook. So you have a textbook chapter in chapter 17 and then chapter 20, I think, which is the reinforcement learning chapter, right? But the textbook doesn't actually talk about a approximate approaches for MDPs. Okay, this one has a lot of things. One of which is actually quite useful, is approximate methods. There's a chapter on approximate methods for MDPs. They will actually give like a 2-page discussion on LRTDP, a 2-page discussion on UCT, and a 2-page discussion on the determinization approach, all of which are their own papers. Okay, so it would be a good chapter to read to make sure that you understand what happens in the approximation cases. And also that way they actually put the several different approximations in one single framework. Okay, and there they actually do talk about the upper versus lower bound and using both of them and considering the data convergence. Okay, this is that bounded RTDP, but we won't talk about that. I'm not sure why we are here. This is general RTDP. Are there any questions that I should talk about for the RTDP? Because you read the paper.
I have one question.
Yes.
How does the LRTDP behave on the cycles? You mentioned that if you have cycle in the graph, so it has different behavior. I was not able to understand.
No, so they were talking about, I guess basically they're comparing it to LAO star there, right? Okay, out of scope right now. Okay, I mean they are essentially, so there are many approximation algorithms for MDPs. Okay, I am not even going to talk about LAO star here. Okay, but I will talk about UCT, which is another approach compared to LRTDP. Okay, and I can give you a paper which compares both of those, for example. Okay. In general, they come up with they are trying to approximate the policy in different ways, and they sometimes have very different trade-offs. Okay. Other questions? Any other questions? I mean, I did not want to answer that because unless I actually describe to you how LAO star works, it doesn't make too much sense. Okay. By the way, this chapter approximate methods does give I think a 2-page description of LAO star 2. Okay. Oh, why is it going so fast? It doesn't seem to want to go to it. Okay. One thing that I want to talk about is the heuristic. LRTDP uses heuristic. You realize that, right? Where does it use the heuristic? It assigns the initial values for the states that way. Okay, so the question is, how does it do it? In essence, basically, the normal value function is the Bellman value function. The optimal value function is connected to the optimal value function of its neighbors by the Bellman equation. Right? Okay. Now, what they're trying to do is set values for the states more quickly than would be needed by actually solving this equation. If you solve this equation, then you can set the values for all the states, but that's kind of very exotic because that's what you're trying to compute. You're trying to compute the optimal value, and then you're computing the optimal value and calling it the heuristic. So those of you who know A star search, it's like saying, if only I get H star, then I can do search very fast. But H star essentially involves solving the problem optimally from every initial state. Not just the initial state you are in, but every initial state. That's an overkill in essence. Okay. Instead, what they are trying to do is they want to somehow approximate this. There are different notions of approximation that are going on here. I am going to be much more aggressive in approximating this to just initialize the values. Once again, in looking at this, if you are thinking of the game tree approach, the game trees where you are essentially trying to figure out which is the move the max player makes. Okay, you wind up needing an evaluation function for the game trees, which will tell you how good are the leaf nodes. If they are not definite wins and definite losses, exactly how good are they? and that can only be approximation, because to exactly find out how good they are, you are supposed to build the min-max tree under them, and then propagate the values up. Instead, you provide some sort of a heuristic approach. So the heuristic approach that these guys provide is quite cute. Okay, let's start by looking at let's say a grid. Suppose our MDP happens to be a grid, and suppose there is a single goal state in the MDP, right? Okay, so one can say that the values for each of these states can be set as essentially something like the straight line distance or the Manhattan distance, right? So you cannot have, and the Manhattan distance, if you think about it, the Manhattan distance would be an actual lower bound on the true cost, right? So if you have deterministic actions, then you would need at least the Manhattan distance to get here. It may be longer even for deterministic actions. With stochastic actions, it will be even longer. Do you see that? Okay, so you could have actually, initialized the values for these states that way. What they're doing, in essence, is, that idea will only make sense if you have something like this, where you can actually talk about straight line distances. The cute thing that they're doing is they are essentially playing directly with the dynamic programming, with the Bellman equation. Okay, rather than compute this, they're computing this. Okay, what's happening there? I'm saying my value is connected to min over the actions I can do, and the cost of those actions, plus here it was the expected value backed up by that action. I expected cost backed up by this action. Here I'm just taking the lowest cost. I just assume the lowest cost will happen. Do you see what I'm saying? Okay. This is a sort of an equation. It's setting up a value of a state to value of its neighbors in terms of this min rather than the expected cost. And then they solve this particular equation. They basically iterate on this. As again as doing the Bellman value iteration, they do iteration on this. So the heuristic is not going to be just a simple function that you can plug in the values and say, oh, this is 15. They actually set the values of the states to something, basically initialized to any zeros except for the terminal state, okay, which has the actual reward, and then you iteratively update the values of the states using this. Okay, in doing so, what you are essentially saying is that they are assuming that they can make the best outcome of each action happen. So this heuristic is delirious. This heuristic is assuming that if I have an action, so the only thing it's not completely delirious about is that it's only considering S dashes, such that there is some action such that you can get to that particular state by that action with a probability greater than 0. So as long as there is a way you can reach a happy state, you assume you will reach that happy state. Do you see what I'm saying? Whereas that's why this winds up being a faster, this is a more efficient computation. But the values you get this way, you can convince yourself that the values you get this way. By the way, in LRTDP, which is basically a stochastic shortest path MDP, when I say value, I mean cost, right? You guys remember that? Okay. So if you set the cost to go of all the states this way, then this cost would be actually the lower bound on the true cost. Because I am delirious, I'm hoping that basically this is, those of you who took 471 with me, you know that heuristics are about having rich uncles who will tell you which direction to go. This is your rich uncle, which is basically saying, well, the action that you're doing will just wind up getting you to the best neighbor, even though there are many other neighbors possible. You see what I'm saying? So in particular, if you have an action A such that it gets you to S dash with 10 power minus 7 probability, and gets you to S double dash with 1 minus 10 power minus 7 probability, S double dash has a cost 15, S dash has a cost 1, you will just assume that you will get to the cost 1 state. And that's what you're going to problem.
So they calculate this heuristic value for all the states in the model?
A heuristic has to be computed for all the states. So before they start the LRTDP, they essentially run this recurrence. They compute a value function. This is a VH.
So that's why when their results is they're comparing the different algorithms, why they have to include the time to calculate heuristic.
Yes, exactly. Okay, but this is just as good an idea in that LRTDP paper. This is basically how do you compute heuristics for MDPs, and what do you mean by heuristics for MDPs? Just initializing the values. Okay, if you don't initialize the values correctly, you will still reach the correct values in the end. It's just the time taken to reach those correct values would be higher versus lower. Okay, so that's one of the things that you should pay attention to in LRTDP. Okay. Okay, so here's actually an interesting question. What if I change this such that I pick the action, the S dash corresponding to the highest probability value?
I think this will be a lower bound.
Will it be a lower bound? What? Why, does anybody see that it won't be a lower bound? That basically is actually what looks like the rational thing to do. Right? If you are going to approximate your action, which has 10 power minus 7 to S dash and 1 minus 10 power minus 7 to S double dash, approximate it such that it gets the most likely outcome rather than the outcome that is best for you. Okay, notice by the way, this one is most likely outcome. Is this least likely outcome? No, it doesn't really care. It will pick whoever is the best, where best is determined by the context. Of all my neighbors, you are the best. I'll assume you will just happen. If you're the best, if you're the most likely, I will take you. If you're the least likely, I'll take you. If you're in the middle, I'll still take you. Do you see what I'm saying? Okay. That's how this heuristic is written. This is indeed lower bound. This, on the other hand, you have to convince yourself is not a lower bound. It's a pretty good heuristic, but it's not a lower bound heuristic. Okay, and again, this is like a lower bound means admissible heuristics. Okay, and one of the interesting things in SSP is if you start with a lower bound value function, and as you do value iteration, okay, it will continue to be a lower bound. Okay, so if you were to pick S dash corresponding to the highest P, that would be what's called the most likely outcome. And that unfortunately won't be lower bound. But one might ask, why do I care about being a lower bound? Anyway, I've given up on looking for optimal policies. I'm trying to look for approximate policies. Okay. The question, of course, is, there are approximate policies which have the guarantee that if you run them long enough, they will actually converge to the optimal. There are also approximate policy algorithms which, even when you run them long enough, they may not converge to the optimal policy. And if you are using this heuristic with LRTDP, okay, then the guarantee of optimality can be lost. Okay. Yeah, so that's kind of what thinking about. In fact, when we get to the determinizations idea, you'll see that both this and this can be also seen in terms of relaxing a stochastic action to be a deterministic one. Okay, because ultimately the real action A can have non-zero probability of transitioning to a huge number of states. This guy is picking just the state that will be the most likely outcome of this action. This guy is picking just the state that is the most optimistic outcome based on the context. Okay, so in some sense what they're doing, under the hood is converting a stochastic planning, a stochastic MDP into a deterministic one. Okay, but this one is a deterministic one too, except this particular determinization. And so when you convert a stochastic one into a deterministic one, the terminology is determinization. Determinization, and in that particular case, if you determinize this way, then you don't have lower bound. If you determinize this way, you have lower bound. But this determinization can be done without looking at the problem, right? Because I can just look at the actions and see, just say, if every action, just pick the most likely outcome, then I have a set of deterministic actions. I just run them now. This, on the other hand, does not allow you that. You need to be able to keep track of all the possible outcomes of the action, and based on the context, pick the neighbor that has the best value at that point of time. Yes?
Would there be any intersection between those two things?
Which things?
Minimum of V dash S and the other way.
No, I mean, sometimes this may wind up picking. It just so happens that your best neighbor also is your most likely neighbor.
So there is a possibility of having an intersection.
Yeah, but I don't know what that means exactly. I mean, in a sense, sometimes, the point is here you are doing it, you're not actually considering, in this idea, which we'll again come back to in a minute, given an action description, you will come up with a deterministic version of the action description upfront, before you even look at the rest of the problem. Here you can't do that. Yes?
What benefit does it produce? Because when you compute mean, then you still have to compute all the neighbors first, right? So isn't it giving you the same cost of computation?
That's exactly the kind of thing, actually, you should just throw this into your reinforcement learning program. I'm asking you to do some things for the code, but you can be much more curious and actually see whether or not this heuristic will help. Okay, one of the very interesting questions about heuristics, and this is a picture that I have drawn for people in 471, which is that you can be spending very little time or a lot of time computing the heuristics. So this is the cost of computing heuristic. And and you can be spending, and then based on the cost of computing the heuristic, you will also have a cost of search. This was a picture that made sense for A star search, but it also makes sense for MDP. Okay, this is cost of computing heuristic and initializing V. And this is cost of computing the policy. Okay, now the total cost that you are basically incurring is something like this. Right? I mean, I don't have a good, okay. Right, basically if you add those up, and then this minimum will be where these guys cross. It's not very, we don't have good intuitions as to where that minimum occurs. It's very much problem dependent. So in fact, people in heuristics in A star search in general, originally people used to think that a heuristic, for it to be good, must take very little time to compute. Okay, anything that seems to take a large fraction of the total search time cannot possibly be a good idea. That's sort of what you are saying, that it's not like this is like a simple plug-in thing. This also seems to require some kind of an iteration. It's an iteration over what I'm trying to tell you is an easier equation which will converge faster, but I cannot show it to you. It's a, you need to run it yourself. Okay, so you guys would have believed me if the heuristic was here. You would have believed me. Yeah, the heuristic will take less time. But one of the problems is if I spend only very little time. So for example, there is a good way which is set value to be 0 everywhere except the goal node for which you set the value to be its reward. That's a way of setting up the value function. And how long does that take to compute? Basically, it's constant time. And that would be somewhere here. But the problem is then when you actually run the LRTDP, by the time it converges, it takes much longer time, so the total is going to be high. You could also, essentially, instead of solving this, solve this equation directly. Set the V to be V star. By the way, what do you think will happen if, unbeknownst to you, this would be a nice question to ask yourself, unbeknownst to you, I initialized your value function to be V star. What do you think will happen to LRTDP? Yes, basically, I mean, still, it basically will very quickly propagate the labels and then say the initial status convergent and stop. You see what I'm saying? It'll do time that is basically proportional to, in the A star search, it will be proportional to just the length of the plan, but here I think it will be proportional to the length of the state space size. Because, actually no, it can still be proportional to the length of the number of states that fall from the initial state to the goal state. Notice that just because there are states in the world doesn't mean you must reach them. Okay, in fact, I think I said this somewhere else. I don't know if yeah, this one. So LRTDP basically only considers the relevant states. Those are the states which will fall on the trajectory from the initial state to reaching the goal state. Because in SSP there is a goal state. Any states, according to the optimal policy, any states that won't fall on that, on that any trajectory with respect to the optimal policy, LRTDP doesn't have to find its optimal value function. It basically ignores them. That's the advantage of essentially doing this kind of a exploration. Okay. So I had a little metaphor there, but in essence, if you have if your optimal policy doesn't touch some states, then you don't need to you don't need to know what to do there. Okay. Okay, so So my point is that V star, if you initialize it to V star, then essentially LRTDP would propagate the labels to the initial node, only touching the states that will fall on the trajectories based on optimal policy from the initial state. So it doesn't have to be all of the state space. Just a second. Okay, and then it's done. Now, that time, the search cost would be very low. But the heuristic cost would be extremely high because you computed the V star to compute V star. I am essentially saying that this is one of the good heuristics. It's somewhere neither here nor there, it's somewhere in
Which one
between.
is better between this one and that one?
Again, so I'm saying that this one actually is not even a lower bound.
Yeah, but in terms of speed, it's not easy to learn.
No. There was somebody else's. I mean, again, I'm trying to hope to get you back into thinking about heuristics, and it's not always the case that one heuristic dominates another heuristic.
But for example, suppose that that one is faster than this one. Yet we can compute the higher bound and the lower bound using something similar to this.
In fact, that is the kind of thing you can do. Unfortunately, this one is not a provable upper bound either. Right. This is a beautiful statement I read somewhere. But this guy fails to be a lower bound. Just because you fail to be a lower bound means you are automatically an upper bound. You can also fail to be an upper bound. In fact, this fails to also be an upper bound. Okay. There are ideas for upper bound that I just skipped over in the previous slides. And if you are into computing the upper bounds, which most approaches don't use, but the approaches that can use the upper bound are the ones that will keep the distance between upper and lower bound to decide how much of a play is there in terms of the value. If the upper and lower bounds are very close, then you pretty much have converged for that state. If they're very far, then you haven't. So in some sense, you want to explore it more. Yeah.
I mean, I was wondering about that, like the comparison between the upper and lower bound, because the Bellman update's already like a contraction operator. Why keep track of both of them as opposed to just the difference between rounds?
Actually, so the thing is that it does not essentially matter even for SSPs. Even for SSPs, you do not have to start with a lower bound. You do not have to start with a lower bound V, right? Because anyway, you will have contraction and you will reach the V star. Okay. However, if you start with a lower bound, you can be sure that you'll always be a lower bound. So your direction of approach to V star is one direction. By the way, that's a very good question. I don't know if people understood what he's saying, which is, unlike A star search, where if you start with an inadmissible heuristic, you can actually find an inoptimal solution. Okay. In value iteration, that's not the case. Because value iteration, the Bellman contraction property holds irrespective of what the value function you started from. It only depends on the fact that Bellman of V star is V star. And so it just, whatever you start from, it keeps getting it closer and closer to V star. However, there are several other good properties of actually having the lower bound, including the fact that if you do that, then you will reach the goal state and reach the optimal value function from one direction. You don't zigzag. Okay. Okay, let me say a little about UCT, which is a slightly different way of approximating MDP value function. Okay, MDP points. Okay. So UCT is first of all, you could use UCT also in times where LRTDP is used. Okay. In thinking of UCT versus RTDP, if you are thinking of this picture, think of RTDP being in this and UCT being here. Okay. But I'll tell you what UCT does in a second. The motivation for UCT is that there can be situations where the actions have essentially exponential number of outcomes. I mean, they have large number of outcomes. An action can have many outcomes. Okay, and if that is the case, then the branching factor in terms of action is extremely high. Okay, now remember the LRTDP pictures. You can go back, but if you remember the LRTDP pictures, if I can have it there. Yeah, so here, assuming that the action has three possibilities. Sometimes there can be actions that can have a large number of possibilities, and you happen to know maybe the probability distribution on all of them. Okay, in such a case, what basically happens is that doing LRTDP can still be quite costly because it is at least expanding each action's outcomes. Okay, what UCT does instead is it just samples the values, samples the outcomes of the actions. So I don't ever have to, so when you have high entropy actions, then I do not want to even consider all possible outcomes of the actions at the same time. Instead, I will just sample the trajectories that I can get. Okay. And if I do that, it turns out, and at each point, essentially, the action just have you're sampling the one outcome of the action without considering what other outcomes it can have. Okay, this comes close to, by the way, reinforcement learning works, right? The way the TD learning works. That's why I said, think of the Monte-Carlo. Okay, in reinforcement learning, and actually, in such cases, basically, you are better off just sampling the future in terms of the trajectories that can happen and using that to approximate the value of the states. Okay, these ideas actually come from what are called the bandit problems, which is, and there's a huge literature on this. The bandit problems are, of course, these are called the one-arm bandits. And you can basically, you're trying to figure out, in this case, just by sampling the bandit, you're trying to figure out which is the best machine to play. Okay, I won't actually go into how the ideas are directly connected, but if you're reading anything about UCT, you will see connections to the multi-arm bandit problems. Okay, so this is our example for UCT. So essentially, for now, just think about the online aspect. Once I know the online one, I can also do the offline. Okay, so I'm at a particular state. Okay, and I'm trying to figure out, I have two actions. Okay, I'm trying to figure out which one to do. Okay, remember I did not say I have lots of actions. I said I have few actions, but each of those actions have very high branching factor. Okay, that's exactly the kind of things where UCT approach is most useful, but it can be used even otherwise. Okay, and it just provides a different set of trade-offs. Okay, so the idea here would be that you would pick, basically, let's say you did this action, and then you randomly selected outcomes. Pick an action, select an outcome of the action until you reach a terminal state. Okay, now the terminal state could be decided, in this case, basically you can actually set the depth of the rollout. Okay, when you reach the depth, that particular depth, then basically consider the value of that state. Now, why do I have the value of the state? It's just an approximation. It may have been initialized upfront. Okay, then I am going to propagate that value upwards. Okay, so if I'm doing this action, I'm getting a 1 in the end. Okay, so it looks like if I do this action, I have a 1 possibility. Now notice, of course, that this is just one sample, It's possible that when I did this action with very high probability, I could have got a very different sample here, or a very different sample here, a very different sample here. The right thing to do is to actually compute the expected value of all of them. However, if I get enough samples, then in essence I'm computing its expected value. You see what I'm saying? Okay. So right now I'm just telling you what happens after one sample. One sample I have this, and then I consider this other action, and then I did one sample, I got a 0. So based on just these samples right now, I visited both these actions at least once. Now, if I must make my mind up, I will basically say this is a good guy. Okay, but now suppose you say, I'll give you more time. You still have more time. You can think a little bit more. Now what do I do? Okay, now I need to essentially, basically sample, basically try to figure out the valuation of each of these actions, to improve them. That's where the idea that you want to think of is consider improving your estimate of those actions and state action phase that haven't been done enough number of times until now. This is corresponding to some question that one of you asked last class. Why aren't we doing exploration exploitation in these problems? UCT directly does a exploration term. Okay. Now the interesting thing is the UCT does have the full model. It doesn't really need to explore. It chose not to use the model directly because it feels that if it were to actually do the action, if it were to look at the action, it has too high a fan out. It doesn't even want to do a single Bellman backup on the entire set of updates, an entire set of outcomes of that action. Instead, it just wants to sample the outcomes of the action. And since it is sampling, it needs to make sure that it has to keep track of which estimates are closer to the right estimates and which are not. And one idea for that, let me get out of this. One idea for that is to keep track of the action. Okay, so this is that so what you're doing is you are finding which particular action to look at. Let me actually look at this second part too. Okay, so after having completed the first part, okay, that is you got one sample here, one sample here, you have decided that, well, this is the best action if I have to do it under right state currently, just based on two samples. Okay, so now I have what is called a partial policy. For this state, I know what to do. And it's partial in more than one way. It's partial because I don't know what to do for the other states. And I also don't know for sure that I'm doing the right thing here. Because this is all based on one sample. Okay, what I'm going to be doing is above this red line is what I think I have an idea of about the partial policy. Below the red line, I have no idea yet. Okay, and so this one I would call it tree policy because essentially, in some sense, in a tree of possibilities, I know which particular direction I'm supposed to be taking. So now I come here. The question is which. So right now I've been given more time. So which one do I spend time on? Do you understand what I'm saying? This is something, by the way, that game trees also deal with. Okay, so here is, by the way, the direct connection to. Let me just say, kind of skip over it. This. How many of you know Go? Wow. Okay, so that's what now, what's the difference for the but what's the difference between Go and chess?
Just between pieces, sort of abstract way of valuing decisions.
So what is the branching factor in Go?
I don't know how to do that.
Like extremely high. It's something I know at least. Okay, so this beautiful. I have a slide down in 1 that like the computer games and okay, so the game that humans refuse to play with computers because humans also refuse to play with machines in terms of it's given. You will be gave up long back. Okay, I'm going to say that's so great. So great. Because you want to play with another brain dead human. It is really not. And I'm going to play. Go computer. The computer go players. Humans regularly refuse to play with them. Again, but it's because they're so stupid. You know what I'm saying? So Go we don't play because the computers are very bad at Go right now. And Othello we don't play because they're very part right now is in chess. Because chess is hard for us, it's also reasonably hard for the machines. Although that's quickly changing. So I think that's why computer chess is still there. There is no computer Go yet, and there is never been any computer Go. Okay? And the reason one reason Go is slow. Go is considered like a holy day in computer games. Okay, now how do you do that? We did chess. How did we do chess? How did you do chess? You basically put the max, you consider all its positions, and you consider all the moves up until some depth. This is nothing but RTDP by a different name. Right? In RTDP, you do backup by expectations. Here, you're doing backup by wins and maxes. This is what we did to win chess. Why can't we do this for winning Go? The problem is that for every move you can make, the number of moves you can make are so many. Actually, it's actually back in the 1D or 2D. You see what I'm saying? However big the tree is, if you don't enumerate the tree, and if you just go through the tree, you can get back without actually running out of memory and patience. So the best approaches for Go right now are based on UC. You see what I'm saying? And so we are now essentially just as RTDP is connected to the fixed depth, big right? UCT is also connected to something like this. Okay? Upper confidence boundaries. That's what it says. This is a Monte-Carlo idea. We're just doing a sample at a time. What is interesting in UCT is the theoretical results are, so anyway, so here, we were right here, so we went this, and so you basically did one probe this way, one probe this way. The same thing you can do if it makes it easier for you to think in terms of chess. You have two moves, let's say, and you considered for one move, you just basically randomly picked a possibility everywhere and saw whether you win or lost, won or lost. So that's like one probe through one action. And this one is another probe through one action. And then based on those probes, you say, hey, that side I seem to be losing, this side I seem to be winning, so I'll just pick the winning one. But then the question of course is how likely is this win and how likely is this loss? That depends on how often have you tried exploring below this. Now in this particular case, since you have explored both of them just once, now if I have to do once more, then what I might do is I might consider coming here one and then re-pick a probe, and then roll out all the way again to the terminal state. This time I got a 0. Okay, so my expected value right now is actually half. Okay, not only that, I also know in doing this, basically, since I'm getting a 0 here, I'm getting a 1 here, I also happen to know what to do under this state now, not just in the previous state. So, in essence, I not only figured out a better expected value for my state, I also expanded my tree policy. So, I happen to know what to do under this state. Okay? And so I continue like this. Now the question is, the next time around, am I supposed to pick this state or this state? And what's the general idea for picking which action to, probe more? And that's where this little formula comes in. And this looks just like your exploration exploitation idea. All this is saying is that you basically would like to pick the action with the highest current QL. Right? Highest current QL. That's what you're doing when I said, I would pick this if I'm here. If I'm here, I would pick this because this is better than 0. Okay. However, I would also keep track of how often I actually come to that state and how often I come back to that state. I don't modify. If this is 2 average, it will be down so it starts to make things have been explored enough look more promising than they really are. Okay. And if they are actual cost values, you will get minus because the cost has to be reduced so that you look good. And this is the part that if you are doing, and there are some good results about doing exploration, this particular form of knowledge. And there are multiple things to do, right? And so I'm just saying, why this particular square of ln of the number of times you got to the state divided by no ln of the number of times you did that action. And the only thing I can say right now is that if you were to do data exploration, there are some nice bounds on how many samples you need to do before you can get some levels of guarantee as close you get to optimal cost. Doing the exploration this way is what makes an normal Monte-Carlo hard to see. Okay, now the interesting thing is that if you know both this idea and UCT, since I told you two things, LRTDP or UCT, and for many problems you can actually do both of them. Which one should be done better? which one should be done. You know. So clearly you can make the problem in such a way that for Go, LRTDP is not even feasible. Only UCT can be done. So if you have an MDP where you have actions which have many outcomes, then UCT is the only feasible game in town. If on the other hand you have few outcomes, then you may as well do LRTDP because this is inefficient. Okay, so the question is which one is better? People are obviously looking, which one is better when both can be done? And there are some interesting studies on that. The interesting point about that is this is from 2012 AAI. So we are coming close to the edge of what we understand about these algorithms right now. Okay. One other idea that I also want to talk about, which I run out of time right now, is the determinization approach. But you will see the video for that and we'll discuss that. Okay. And I'll see you Wednesday after the next Wednesday.